All right, ready to dive in. Today, we're looking at federated learning and specifically how it can be used to protect data privacy.
Sounds fascinating.
Yeah, so imagine like you're using some AI, helps you write your texts, but the company, that made it never actually sees any of your personal messages.
Oh, wow, that'd be amazing.
That's the promise of federated learning.
So how does that even work?
Well, instead of like sending all your data to like some central server, the model actually comes to your device, learns from it, and then only sends back like the little updates it made.
So like in this paper we're looking at, my phone, it downloads a basic model, like for predicting the next word,
Right, exactly.
and then it would just train on my messages. So it's getting smarter about what I type, and then it sends back a few tweaks, but like my actual messages, they'll stay on my phone.
Yeah, exactly. It's like my phone is contributing to this global model, but it's not like spilling all my secrets in the process.
That's pretty cool.
Yeah, but here's where things get a little tricky.
Ah,
Even though you're not sending the raw data, those model updates, they seem harmless, but, they could still leak sensitive information.
like what?
Well, theoretically, someone could reverse engineer those updates and figure out specific words you typed.
Oh, so it's not as private as it seems on the surface.
Right, exactly. But this is where the paper brings in this really cool idea called secure aggregation.
Secure aggregation.
Yeah, so it's this cryptographic technique that basically lets everyone like contribute to the model's learning, but without revealing what their individual updates were.
So it's kind of like we're all bringing ingredients to this big potluck, but nobody knows who brought what, just the final dish is, delicious.
Yeah, that's a great analogy. The server, it only sees the combined result, not the individual ingredients. But actually getting this to work reliably, well, that's the real challenge.
Right, I bet.
Yeah, so the authors of this paper, they actually walk us through like a whole series of protocols, each kind of building on the last to address different problems.
Oh, that's a great approach. Like start simple, then get more complex as you solve problems.
Exactly. So where did they begin?
Well, they start with this like deceptively simple idea. What if they just mask their updates with some random noise?
Noise, like just random data.
Yeah, but it's like specially designed noise. Like
Mm.
it's designed to magically cancel out when it's combined with everyone else's noise.
Oh,
They
okay.
call this protocol zero or masking with one-time pads.
So it's kind of like everyone's speaking in code, and only when you put all the messages together do you get the real message.
Yeah, that's the idea.
Hmm.
And it offers perfect privacy because the server learns absolutely nothing about what any individual update was.
Okay, that sounds almost too good to be true. Is there a catch?
Of course there's a catch.
Yeah.
The big problem is this approach is, it's really fragile. Like imagine one person forgets to bring their dish to that potluck we were talking about. Suddenly, everything's off right.
Oh, yeah, I see.
So if a single user drops out, like their phone disconnects or something, the whole system breaks down. Because all that carefully calculated noise, it doesn't cancel out anymore.
So it's not very practical for the real world where people are always connecting and disconnecting.
Exactly, especially on mobile devices. Protocol zero, it's like a house of cards. It could just collapse at any moment.
So what's the next step? How do they fix this dropout problem?
Well, that's where Protocol 1 comes in, which is all about using something called secret sharing.
Secret sharing. Now that sounds interesting.
Yeah, we'll dive into that right after the break.
All right, so secret sharing. What's the secret? How does that make this whole system more robust?
Okay, so imagine instead of, one person bringing a whole dish to our potluck, they split it into pieces
Okay.
and they give like a piece to everyone else at the potluck.
Oh, I see.
So even if someone like leaves early, you can still kind of combine the remaining pieces to get a pretty good idea of what the original dish was.
Ah, that's clever. So even if some users drop out, as long as enough of them are still around, you can kind of piece together that missing information.
Yeah, exactly. And that's how they handle those dropouts. So each user, they split their random noise into these shares, and then they distribute them to other users.
Okay.
So that way, even if there are some dropouts, the system can still like recover the missing noise and make sure that the aggregate update is still correct.
That's really cool. It's like a safety net for the noise.
Exactly. This protocol, it introduces like public and private key pairs
Oh.
so that users can, communicate securely, but it still relies on the server to kind of coordinate everything.
Okay, but I'm sensing another but coming. Does this secret sharing, does it mess with the perfect privacy we had before?
You're right to be skeptical. Unfortunately, it does.
Ugh. So we solve one problem, we create another. It never ends.
Well, that's the challenge, right? So by introducing this secret sharing, the system, it it becomes vulnerable to a malicious server. If the server was, dishonest, it could try to manipulate the process, try and uncover those individual updates.
Oh, man. So we went from a fragile system to now a system with a potentially sneaky server. What's next? How do we deal with that?
Well, the researchers, they thought about that too.
Yeah.
And they came up with another clever trick. They called it double masking.
Double masking. That sounds intense.
It is. It's like adding an extra layer of security to those secret ingredients we were talking about.
Okay, so walk me through this.
Okay, so in Protocol 2, which is, they call it double masking to thwart a malicious server, what happens is the users, they add a second random mask to their updates.
Okay.
And this mask, it's only revealed if the server tries to do something, sneaky, like reconstruct someone's individual contribution. It's kind of like an alarm that goes off if someone tries to peek under the lid of your dish at the potluck.
So even if the server tries to isolate one user's update, it just hits a wall of randomness.
Exactly. It's a way to restore that security even when you can't fully trust the server.
Oh, okay, that's pretty clever.
Yeah, but it gets even more interesting because they realize that, how much protection you need, it really depends on how much you trust the server.
Oh, okay.
So, they outline these different threat models, and each one requires a different level of security.
Threat models. So, how sneaky are we assuming the server is being?
Yeah, exactly. So the first one is like an honest but curious server.
Honest but curious. Okay.
So it follows the rules, but it tries to learn as much as it can from the data. Think of it like a server that, respects your privacy, but might be tempted to analyze the data in aggregate.
Okay, that seems like a reasonable baseline.
Yeah, and then the next level up is a server that could lie about, like which users have dropped out.
Oh, so now it's not just curious, it's actively trying to mess with the system.
Exactly.
Yeah.
And that gets more dangerous because the server, it could manipulate that secret sharing process we talked about.
Okay, and I'm guessing there's an even worse scenario.
Oh, yeah, there is. The most challenging one is a server that can both lie about dropouts and has access to, the private memory of some users.
Wow, that's super malicious.
Yeah, so that's the worst case scenario, and it requires the strongest security measures.
Okay, so basically, the more we distrust the server, the more robust our security has to be. It's like a sliding scale of paranoia.
That's a great way to put it. But all these security measures, they come with a cost. Robustness is great, but if the system gets too complex, too inefficient, it's just not going to be practical in the real world.
Right, especially if we're talking about running this on a phone. You don't want to drain everyone's battery just to send a text message.
Yeah, exactly. And that's where Protocol 3 comes in. It's all about, exchanging secrets efficiently. Remember all those secret keys being exchanged? Well, it turns out that can generate a lot of data, especially when you have, tons of users.
Oh, yeah, that makes sense. So how do they slim things down?
They get clever with the key management.
Yeah.
So instead of generating a unique secret key for every other user, they use a technique called Diffie-Hellman key agreement.
Okay.
So each user, they generate just one secret key and a public key. And then they share that public key with the server.
Okay.
And this allows any two users to establish a shared secret key without actually directly talking to each other.
Oh, wow. So it's like cutting out the middleman, but in a secure way.
Yeah, exactly.
Yeah.
Less chatter, more efficiency.
And what about all that random noise? Do they do anything to streamline that too?
They do. So instead of sharing this huge vector of random values, they use a much smaller, what they call a seed value.
A seed value.
Yeah, and then they use a tool called a pseudo-random generator to expand it. It's kind of like compressing a file before you send it and then decompressing it on the other end.
So they're basically packing all that randomness into a smaller package.
Exactly. And that saves a ton of bandwidth, but without compromising on security. So now we have this system that's more robust against dropouts, protected against a malicious server, and efficient enough to run on, everyday devices. We're getting close.
Awesome. So are we done? Is that the final protocol?
Almost. But there's one final hurdle, and that's, the real-world limitations of noble devices.
Wait, what do you mean? I thought we've been talking about phones this whole time.
Yeah, but up until now, we've been assuming that these devices have, perfect secure channels for communication.
Right.
Which, let's be honest, just isn't true in the real world.
Yeah, because anyone could be eavesdropping on those communications.
Exactly.
So how do they deal with that? So no more assuming phones have perfect security. What happens when you have to deal with the real world?
Well, that's where Protocol 4 comes in. It's all about minimizing trust in practice. You see, they acknowledge that mobile devices just don't have these like super secure channels we've been talking about.
Right.
So instead of trying to create something that doesn't exist, they propose a system that minimizes the amount of trust that's needed.
Okay, hold on. Minimize trust. But haven't we been trying to protect against this, like, potentially malicious server this whole time?
You're right to be concerned. And yeah, this new approach, it does involve the server in the initial key exchange process. It's a trade-off, but the authors argue that, it's unavoidable in the real world.
So we're putting some faith in the server, but with the understanding that our phones just aren't equipped to handle these super secure channels on their own.
Right, exactly. And to mitigate that risk, they've designed this initial key exchange to be really simple and transparent. It could even be, like, audited by a third party.
Okay, so it's not a perfect solution, but a practical one. But does it still offer any real protection?
Oh, absolutely. It's still far more secure than having no protection at all. And importantly, it provides something called forward secrecy.
Forward secrecy. That's a new one. What is that?
Basically, it means that even if the server were to be compromised in the future, an attacker wouldn't be able to decrypt past communications.
Oh, wow.
So your data remains protected, even from, like, future threats.
That's a relief. So after this whole deep dive into secure aggregation, what's the big takeaway? What makes this research so interesting?
Well, what excites me is that this isn't just theoretical. They've actually laid out, like, a blueprint for a system that can be implemented in the real world.
Right, because super secure system is useless if it's too complicated to actually use.
Exactly. This paper shows that secure aggregation can be practical, and that opens up all sorts of possibilities.
Like what?
Well, think about secure voting. Imagine a system where you could verify that your vote was counted, but no one knows who you voted for.
That would be amazing.
Or even medical research. Secure aggregation could let scientists analyze sensitive patient data without compromising anyone's privacy.
So we could have all these medical breakthroughs while still protecting people's privacy.
Exactly. It's about changing how we think about data privacy, especially in a world that's so reliant on data.
This has been an amazing deep dive. We've gone from like the basics of federated learning to all the little details of secure aggregation.
It's been a pleasure. And of course, this was just a taste of what the paper has to offer. You can find a link to the full paper in the show notes.
Yeah, definitely check it out. And as you do, here's something to think about. Could secure aggregation be the key to a future where we can benefit from all this amazing technology without sacrificing our privacy?
It's a question worth pondering.
Thanks for joining us for this deep dive. Until next time.